Okay, so now that we've talked a little more about elements and their symbols and names, let's focus on the atoms part of this chapter on atoms and elements. Alright, so here we are ready to dive into the atom, and hopefully you've already had this in a prior course, but if not, we'll take it from the most basic level, and we'll talk about some theories of the atom from early on that are a little easier to wrap our minds around than how we currently understand the atom. Now, there were some ancient world ideas about matter that involved atoms. So Leucippus and Democritus had atomic theory way back when in ancient Greece, but they really didn't have any scientific evidence. They didn't do the experiments that they couldn't do at their time that we can now to prove it. And so that atomic view of matter did not win out because Aristotle took a continuous view of matter, and of course it's difficult to compete with the brilliance of Aristotle. So the first time we had a legitimate atomic theory, a scientific atomic theory, was Dalton's atomic theory back in the 1800s. And Dalton theorized that atoms, here are what we call the postulates of his theory. First of all, they're tiny particles of matter too small to see with the naked eye. They're able to combine with other atoms to make compounds, and they're similar to each other for each element and different from atoms of other elements. So not bad. He's pretty much dead on. He, overlooked a couple of things, but for an early atomic theory, it's pretty solid. And so Dalton understood chemistry and chemical reactions to be the rearrangement of atoms. And here we see a scanning tunneling microscope STM image of some nickel atoms. And so nowadays we can image the atom with electron microscopes and atomic force microscopes. So we're quite a bit more advanced than where Dalton was, and certainly where Leucippus and Democritus were. All right, so one of the problems with Dalton's atomic theory is that the whole reason he came up with the name atom is that literally means a, like asexual, meaning without. So without, or that which cannot. Tome means to cut. So according to his theory, atoms were the smallest part of matter, and you could not cut them into anything smaller. Of course, nowadays we understand that there are subatomic particles, and you can go below the atom, but once you get subatomic, you no longer have the characteristics of that element. So an atom is still important because it's the smallest piece of a particular type of matter, a particular element. So once you go below the atom, you're no longer unique to that element. You're dealing with things like the protons, electrons, and neutrons we'll describe, which are present in all atoms. So that is still an important distinction for the atom. The atom is the smallest unit of an element. However, all atoms contain certain subatomic particles: protons, which have a positive charge, electrons, which have a negative charge, and aside from hydrogen, which doesn't have any neutrons in its most popular isotope, most elements do have neutrons, which have no charge. So experiments show us that like charges repel and unlike charges attract. So it's interesting that matter is divided up into these positive nuclei. The protons and neutrons we'll see end up in the nucleus, and the electrons outside. You'd think that the electrons would just want to pair up with the protons and matter would collapse on itself. Fortunately, that's not how it works, but we do have to consider the interplay of electrons and protons in order to describe the reactivity of different atoms. Okay, so we have Dalton's atomic theory, and we have sort of a plum pudding model. We knew about the positive charge and the negative charge, but Dalton postulated that the negative charge and positive charge were sort of evenly dispersed throughout. And so Ernest Rutherford set out to prove that idea with his famous gold foil experiment, and instead he made a very important discovery. And that was that the positively charged particles, these protons, were densely populated in a small nucleus, and that we have the electrons diffusely spread out outside of the nucleus. So he bombarded this gold foil with some alpha particles, as we'll see in the next slide, and he saw that most of the time they went straight through, which indicated that atoms are mostly empty space, but sometimes they were deflected, and sometimes they were deflected at very large angles, which made little sense for these massive particles. So that's how we came up with the conclusion that there must be a small, dense, positively charged nucleus that could deflect those positive alpha particles when they got close. And here we see a nice graphic showing that. So there was a source of these alpha particles, and it was contained in this lead container to keep the alpha particles from going any other direction. So there was a small hole to direct that beam of alpha particles toward the gold foil. And then there was a detector, a fluorescent screen that would detect those alpha particles after they've interacted with the foil. And as we see, most of the time they went through undeflected because they weren't interacting at all with the nucleus. But occasionally, if they got close to the nucleus or if they hit dead on with the nucleus, they could be deflected. And so the fact that that happened rarely suggested that these positive protons, which would deflect the positive alpha particles, must be very small and very dense. And the rest of the atom must be essentially empty space. And so that's an important first step, moving away from the plum pudding model that Thomson actually had. It wasn't our good friend Dalton. He didn't come up with that model. It was Thomson that had the plum pudding model that was later replaced by this nuclear model of the atom that Rutherford's experiment helped to prove. Or at least helped to suggest, I suppose is a better word than prove in science. Alright, so the take-home message is based on Rutherford's experiment and other similar experiments. We have the knowledge now that, at least according to our more modern atomic theory, we understand an atom to consist of a nucleus that has the protons and the neutrons, and then the electrons exist outside the nucleus in a large empty space. They give the atom its volume. They're small particles, but they move very fast, and they define the volume, whereas the small, dense, massive particles, the protons and neutrons, exist inside that small nucleus. If we want to think about the mass, the atomic masses, again, are based on number of protons, neutrons, and electrons. It's mostly based on the proton and neutron masses. So for our definition, we need a stable nucleus, and so therefore carbon-12 has been selected. Oxygen-16 actually used to be the reference atom, but now it's carbon-12, and one atomic mass unit is defined as 1/12 of the mass of a carbon-12 atom. So if we look at the mass of a proton, it would be a mass of about 1 atomic mass unit, to be exact 1.007 atomic mass units. The mass of a neutron is about 1 also, a little more massive, 1.008 atomic mass units. And an electron, as we said, it's a very light particle, very small mass, oftentimes essentially given a value of 0 atomic mass units, but it does indeed have a mass, and here we see it's 0.00055 atomic mass units. And the relative mass of an electron is about 1/1836th the mass of a proton, so about 1/2000th the mass of a proton. So very, very light and very small in comparison, with protons, and then neutrons are just a little more massive. And when we talk about radioactivity, we'll mention that neutrons are sort of like protons and electrons combined, so that's one reason they have a slightly larger mass, but we'll save that for our discussion of radioactivity. And here table 3.5 summarizes the subatomic particles of the atom very nicely. The proton, neutron, and electron. We see the symbols for proton, either a P or a P with a positive superscript to remind us about that positive charge. Neutrons, usually just a lowercase n, or sometimes an n with a 0 superscript to remind us about its neutral charge. And then finally, electrons are typically denoted as a lowercase e with a superscript minus to remind us about their negative charge. And then obviously the electrical charge and the mass we've discussed. And the protons and neutrons exist inside that very small, dense nucleus, while the electrons exist well outside the nucleus. If our nucleus was a golf ball on the 50-yard line of a football stadium, the electrons would be out of the stadium into the streets of the city. That's how far apart the electrons typically are compared with the nucleus. Okay, so before we leave our topic of the atom, we have a learning check here to make sure that we're getting those key concepts. So in this learning check, you're going to identify each statement as describing a proton, neutron, or electron. So for the first description, this subatomic particle is found outside the nucleus, and you may have more than one correct answer for these. Number 2 has a positive charge. Number 3 is neutral, and then number 4 found inside the nucleus. So go ahead, if you haven't already made your assignments, pause the video, and we'll pick up and see how you did. Okay, so let's take a look. Hopefully you were able to identify that the subatomic particle that's found outside the nucleus is the electron. The subatomic particle that has a positive charge for number 2 is the proton. The neutral subatomic particle from that list. Of course, there are smaller subatomic particles. We don't get into quarks and leptons in this course, but of the 3 that we've learned, the neutral particle is the neutron. And number 4, both protons and neutrons can be found in the nucleus of the atom. So hopefully that went well. Otherwise, just review again, try a couple end of chapter problems, and as always, get in touch with me if you're having real conceptual difficulties.